This video is sponsored by Ground News. One of the biggest mysteries in the entirety of astrophysics is how do supermassive black holes form and then grow to be so supermassive? But a research paper by Bogdán and collaborators has come out this month claiming to have solved this. Now, perhaps I am a little bit biased because supermassive black holes are my area of research, but I just find this so fascinating because the only process that we know of that can form a black hole is a supernova. When a star runs out of fuel and its core collapses down under gravity to form a black hole anywhere from 5 to 100 times heavier than the sun. But these supermassive black holes that we find in the center of galaxies are anywhere from 1 million to tens of billion times heavier than the sun. So if a supernova is the only process that we know of to form a black hole, then to get something supermassive, you have to grow it from, say, a few tens of times the mass of the sun up to 1 million, 1 billion times of the mass of the sun. Now, in the nearby universe, where we're seeing things that have had 13.8 billion years to grow to become that big, that makes sense. That's more than enough time to grow a black hole. But we also see supermassive black holes in very distant galaxies where the light has taken so long to get to us that we're seeing them when the universe was only 700 million years old. Which for those to exist and be 1 billion times heavier than the sun and have grown that big in, say, just 700 million years, they would have had to grow at faster than the maximum limit at which a black hole can grow at. They shouldn't exist. And that's the unsolved mystery. How do supermassive black holes grow so big so quickly? Is there perhaps another way that we can form black holes in the early universe? One that gives you a little bit of a head start on that growth process and forms a black hole much bigger at, say, 1,000 times the mass of the sun. And that's what Bogdán and collaborators claim to have found evidence for in this research paper they've published this month. So in this video, we're going to chat first about the different formation theories for black holes, including this idea of a direct collapse black hole. Second, how Bogdán and collaborators have claimed to have found the most distant black hole known using gravitational lensing and X-ray data. 3, how they then calculated the mass of that supermassive black hole and the mass in stars of the galaxy it lives in. 4, why the ratio between those two masses gives evidence for direct collapse black holes. And finally, we'll just chat about some caveats on this result and what's next for this research field. Now, some of you might have seen this research covered in the media already, especially if you tend to read center-leaning media outlet sources. If you prefer a left or a right-leaning media outlet, there's a chance you might have missed it. And the reason that I'm able to see this breakdown by political bias is thanks to my Vantage subscription with the sponsor of today's video, Ground News. Ground News is the brainchild of former NASA aerospace engineer Harleen Kaur. She created this app and website that gathers all the world's media in one place, so readers can compare coverage and get the full picture, right, with a visual breakdown of news outlets, political biases, the funding sources of a publication, and also which countries are covering the story. And the reason that I particularly love Ground News is because it takes away the sensationalism that's become so common in the modern media market, especially for science coverage. So I use Ground News to stay up to date with how the media are covering mine and my colleagues' research papers, which Ground News makes so easy because it's got these interest pages for things like space and JWST and NASA. So if that sounds like something you'd be interested in, then now is the time to sign up because Ground News are having their biggest sale of the year. You can get 40% off their Vantage subscription, which gives you unlimited access for just $5 a month. So head to ground.news/Dr. Becky before the sale ends on the 30th of November, or you can click on that link in the video description below. So thanks again to Ground News, and now let's get back to science. And let's start by chatting about the formation of supermassive black holes. And essentially what this all boils down to is the seed mass for your black hole that you start with. A supernova gives you a light seed, between 5 to 100 times the mass of the sun. But what if you could have a heavy seed at around about 1,000 times the mass of the sun that gives you a bit of a head start on your black hole growth? The idea being that clouds of gas in the early universe could collapse straight down into a massive black hole, skipping making stars and one of them going supernova just entirely in a process that's known as direct collapse black holes. I like to think of it of sort of like the astrophysics chicken or the egg, right? Did a cloud of gas in the universe collapse and form a load of stars and become a galaxy, and then one of those stars go supernova, form a black hole, and it became the supermassive black hole at the center eventually? Or did the cloud of gas directly collapse down into a black hole first, and then a galaxy of stars form around it? I've actually made a whole video before about direct collapse black holes. If you want to check that out, I'll link it in the video description down below. But I also cover this in a bit more detail in my public science book, A Brief History of Black Holes, which is out now worldwide in paperback if you want to grab a copy. And the whole reason that this idea of a direct collapse black hole was raised in the first place is because we found supermassive black holes 1 billion times the mass of the sun in galaxies that we see when the universe was just 700 million years old. And to grow from a light seed black hole formed in a supernova to 1 billion times the mass of the sun in under 700 million years, they would have had to have grown faster than the physical limit that a black hole can grow at, known as the Eddington limit. So as matter gets close to a black hole, it orbits around it at huge speeds and it starts to heat up, and therefore it glows in all different types of light, from optical light, infrared light, UV, and in X-rays. But that means it gives out energy that pushes outwards on any other matter falling in. And as more matter falls in, it glows more, it gives out more energy, and therefore there's more pushing back on the material falling in. And at some point you reach this sort of happy medium where you can't get any more material in because there's all the material being pushed out in what's known as an outflow. That limits the amount of material that can get down to the black hole, and therefore the rate at which a black hole can grow at. And if you run the maths, you find that that limit depends on how massive the black hole is. And as it gets bigger, it can grow at a faster rate, but that rate is still limited, which is why you can't grow a black hole from a light seed from a supernova up to 1 billion times the mass of the sun in just 700 million years. But if you start with a heavy seed mass from a direct collapse black hole at around about 1,000 times the mass of the sun, then you can grow a black hole up to 1 billion times the mass of the sun in less than 700 million years. No problem. You don't reach that physical limit. And so you'd think, great, right? Problem solved, except for the fact that we still don't have any evidence that a direct collapse black hole is even possible. Simulations suggest that they are, but we've never observed anything in the universe that supports that idea, which is why this still remains an unsolved mystery. At least that is, until this month with this new research paper published by Bogdán and collaborators. And they claim to have found an even more distant supermassive black hole that they say its properties can only be explained by a direct collapse black hole scenario. So let's chat now about how they even managed to find this distant galaxy with a growing supermassive black hole. Well, it starts with an image from JWST of the galaxy cluster Able 2744, which has been nicknamed Pandora's cluster. It's a group of a few hundred galaxies all bound together by gravity, relatively nearby at about 4 billion light years away. But in the background of this image, Castellano and collaborators also found 11 extremely distant galaxies, found thanks to something known as gravitational lensing, where the massive foreground galaxies in the cluster act as a lens, bending space itself to change the path of the light from the background galaxies to magnify them, make them brighter, and therefore easier to spot. They are incredibly distant. The light from these galaxies has taken over 13 billion years to get to us, so we're seeing them when the universe was just 500 million years old. So once these 11 galaxies had been found, Bogdán and collaborators then wanted to know if any of them contained a growing supermassive black hole. So they looked at the same cluster of galaxies with NASA's Chandra X-ray telescope. Because X-rays are ubiquitous with growing black holes, not just with supermassive black holes, but with black holes in our own galaxy, the Milky Way, as well that are much smaller, formed from a supernova. And the difference is really that, the lighter black holes, they give off less energetic X-rays than the much larger supermassive black holes, where the X-rays are incredibly energetic that they give off. But you can also get X-ray emission from the hot gas between galaxies in clusters as well. So when you look at Able 2744 with the Chandra telescope, first of all, what you see is just this big amorphous blob of gas in the cluster. But the key is that we already know where the really distant galaxies are thanks to JWST. So you can look at those specific locations and see if you find an excess of X-ray light that's above that background glow of the cluster. And Bogdán and collaborators only found an excess for one of those 11 distant galaxies, one that's known as UHZ1. And you can see the excess in this image. So first of all, the black contours in the center there are what JWST detected in the infrared of this incredibly distant galaxy. And if you're wondering, well then what's all these colored squares? Each square represents a pixel of the detector on board the Chandra telescope. So you're seeing the X-ray data here, where you've got a black or a purpley square, that's where there's less X-rays been detected, whereas a yellow colored pixel is where more X-rays have been detected. And you can see here that yellow splotch in the middle lines up really nicely with the location of the galaxy found in the JWST data. Now I know what you're probably thinking is that the Chandra data is such low resolution in comparison to JWST. And yeah, you'd be right. One pixel on the Chandra detector is 0.492 arc seconds across, whereas the JWST NIRCam pixels are 0.03 arc seconds across. So yeah, the Chandra resolution is 16 times worse than JWST. This once again just highlights the incredible power of JWST from the massive mirror that it has to collect light at 6.5 meters across. It can just see so much more detail. But even despite that low resolution of Chandra, the distribution of X-rays that you see here across the pixels is consistent with the X-rays coming from a single point source of light, like from a supermassive black hole, rather than like an extended source of emission. If it was coming from the whole galaxy, for example, they'd be much more smeared out. Bogdán and collaborators claim this is a 4.2 sigma excess of X-rays over the background level, which to translate that stats jargon means that there's a roughly 1 in 40,000 chance that the detection they've made is just a statistical fluke due to random noise. So it's a significant detection that they've made, one that Bogdán and collaborators are pretty confident of. Which brings me to part 3, how Bogdán and collaborators then calculated black hole mass. Well, the amount of X-ray light that you detect from a black hole is dependent on 3 things. First of all, how much material is there orbiting the black hole that's actually glowing? How fast is the black hole growing at? How much material is it taking in? Second of all, how much dust is in the regions around the black hole? Because if you do have a lot of dust, it can actually reflect a lot of X-ray light back at you, making it appear brighter than it actually is. And then third, how fast that material is actually orbiting around the black hole. Because the bigger the black hole, the higher the speed it can accelerate that material to. So if you want to work out the mass of the black hole, then you can use the X-ray brightness. You've just got to make a lot of assumptions about how much dust is there and at what rate the black hole is growing at. So at first, Bogdán and collaborators assumed that the black hole in UHZ1 was growing at the maximum rate possible and that there was no dust blocking any of the light. And with that, they got a mass of 1 billion times the mass of the sun. However, that is larger than the mass in stars of the galaxy. So Castellano and collaborators earlier this year in 2023 looked at the amount of infrared light detected by JWST to work out the mass. And we can do that because if we see some population of stars in the Milky Way, some smaller, some heavier, and they've got a typical spread in masses, and therefore we know how much they would all weigh collectively, we then know how much light they all give off collectively. We can say, okay, if we detect this much light in a distant galaxy, we know roughly that there's this amount of stars, this mass in stars that's giving out that light. And when Castellano and collaborators did that, they found that UHZ1 was around about 40 million times heavier than the sun, which means the black hole is heavier than the galaxy of stars around it. That is really weird. Weird and interesting, which brings me to part 4. Why this mass ratio gives you evidence for a heavy seed of black hole formation, these direct collapse black holes. Now, first of all, we just got to say, yes, the early universe could just be very weird and very different to what we see in the nearby universe, and that could explain this. But to just give you some context on why it is so weird to find a black hole much heavier than the galaxy of stars that it's in. Typically, when we look at galaxies much nearby, we see this correlation between the mass in stars in a galaxy and the mass of the supermassive black hole. And you find that the supermassive black hole tends to be around about 0.1% of the mass of its galaxy, not 150% like UHZ1. So Bogdán and collaborators point out that the mass they calculated is not very likely. So it's likely that there's some dust reflecting light back at us, and also that the supermassive black hole is not accreting at its maximum rate. So there's probably a range of values that you could have in there. And so if you take all those things into account, Bogdán and collaborators then get a range of values from 10 million to 100 million times the mass of the sun for UHZ1's black hole mass, putting it at the same mass overall, roughly, as the amount in stars in the galaxy. So the fact that this black hole is somewhere around, if not larger, than the amount of mass in stars in the galaxy suggests that it was the one that formed first, and then the galaxy of stars around it. So probably as a direct collapse black hole. Not only that, but if you also look at what rate you would have to grow the black hole at to reach these masses in just 400 to 500 million years of the universe's lifetime, you find that if you start from just the light seed black holes formed from a supernova, which is shown in the solid blue here, you can't reach that mass if you grow constantly at the maximum rates allowed. You have to grow above the maximum physical limit, as shown by the blue hatched region there, to reach those masses in that time. But if you start from a heavy seed, which is shown in the orange there, with a black hole formed by a direct collapse, and you grow it at the maximum rate that's physically possible, you can reach that range of masses in the time that you have. So that, combined with the fact that they are very similar masses, leads Bogdán and collaborators to argue that what they've seen here is evidence for direct collapse black holes in the early universe, and then the galaxy of stars forms around them, slowly building up its stellar mass to give us sort of the mass ratios that we see today. So it's a really exciting result, one that seems to solve this astrophysics chicken or the egg question. But what are the caveats here, and what's also next for this field? Obviously, the biggest source of uncertainty and the biggest caveat here is that mass of the supermassive black hole. We just don't know how much dust is there surrounding the black hole, what rate is it growing at, and we don't even know what the conditions are like in the early universe yet, because we just don't have those observations to tell us. So it's likely that that black hole mass could change. It could even be much lower than estimated. But I don't think that even with all these caveats, it would reduce in mass enough so that it could be explained by a maximum growth rate from a light seed. Another problem, though, could be the estimate of the mass of stars in the galaxy. We know that this is a huge problem right now as we start to get more and more JWST data. It seems as if very distant galaxies are more massive than we expect them to be. So are we perhaps overestimating the masses of very distant galaxies? Again, I've made a whole video on this before. If you want to check it out, I'll link it in the video description down below. But if that's the case and we are overestimating the mass of this galaxy, then that ratio between the black hole and the mass in stars just gets even larger, making that scenario of a direct collapse black hole even more likely. But by far, the biggest caveat to this whole study is that the galaxy might not be as far away as we think it is. So Castellano and collaborators used JWST images to spot the reddest galaxies that the light has been stretched so much by the expansion of the universe that we only detect it in images taken with the longest wavelengths of light. They specifically look for galaxies that aren't detected in images at the shorter wavelengths because you get this huge drop off for very distant galaxies. It's not a perfect method though, because that drop off that lets you pinpoint the amount that the light's been redshifted by, and therefore how long it's been traveling for and how distant that galaxy is, can happen anywhere in that range of wavelengths that the filter that you've chosen to take an image actually lets through. Ideally, what you do is get a spectrum where you take the light, split it through a prism, and get a trace of how much light each wavelength you receive. That way you can then pinpoint that drop off much more accurately. And we have had examples where we thought we'd found very distant galaxies in JWST images, but then when we've taken a spectra of the same galaxy, it just turned out to be a much more nearby galaxy, like masquerading as a very distant one because it had a lot of dust, for example, that was absorbing the light at much shorter wavelengths. For example, in this work by Arabal Harrow and collaborators that came out earlier this year in 2023, they had a galaxy that was first thought to be a redshift factor of 16. So the light from the galaxy coming from when the universe was just 240 million years old, but the spectrum revealed that the redshift was actually just 4.9, so the light was coming from a galaxy when the universe was just 1.2 billion years old. So we are going to need spectroscopic follow-up of UHZ1 to confirm that it is actually at the distance that we think it is, so that we can pinpoint the time in the universe's history that we're observing at, because that is key here, because it might not be 500 billion years, it might be more like a billion years if it is actually much closer to us, that time that we, have to grow the black hole in. Now, Castellano and collaborators have actually applied for follow-up spectra to be taken with JWST on the Able 2744 distant galaxies that they found in the most recent round of proposals. They were awarded time again, but it looks like only 6 galaxies are going to be targeted, and UHZ1 is sadly not one of them. But given the results of Bogdán and collaborators for UHZ1, I think this is going to be high up on the priority list for the next round of JWST observations to get spectroscopic follow-up of UHZ1. Plus, I think there's going to be a lot of renewed efforts to get X-ray data for other JWST deep fields, like, for example, the Sears imaging data, where they've also found a lot of high redshift, very distant galaxy candidates, with the goal of finding more of these growing supermassive black holes in the center of these distant galaxies, so that we can again work out their properties and see if they also support this idea of direct collapse black holes in the early universe. And essentially what this all boils down. Do you think now we have this stronger evidence for direct collapse black holes that Muse would think about re-recording supermassive black hole as direct collapse black hole in honor of it? That feels like something they would be up for, right? That'd be fun. Maybe it's just me that thinks it's fun. Collapse black hole is even possible. Simulations, cool result. One that seems to solve this issue of the astrophysics chicken or the egg. I think what happened there was astrophysics and chicken just smushed into one, so it became astrophicken. Was it over when she lay down on